Hi, in this video we're going to be talking about the alternating series test. Now an alternating series is something of this form. It's some alternator times some function of n. And an alternator just flips the sign. So it could be -1 to the n, -1 to the n plus 1, or in general -1 to the n plus some integer. And those are the common alternators. But there's also some weird ones that perform the same function. For example, cosine of n pi gives us a alternating thing because for n equals 1, we have cosine of pi, which is -1, and then for n equals 2, we have 1, 3, -1, 4, 1, and so on. So this is actually another type of alternator that you might see in your series. And now that we know what an alternating series looks like, let's look at the alternating series test. Now, the alternating series test is pretty easy to understand. What it says is if I have the sum, let's just call it -1 to the n, under the understanding that it's just an alternator times a sub n. And if the following two conditions are met, then it converges. So if an is decreasing, and 2, if the limit as n goes to infinity of an is equal to 0. So it has to be decreasing, going to 0, and then if we have that alternator, then what happens is the sum of -1 to the n of an converges. Okay. So that's it. That's all the alternating series test is. So let's look at a couple of examples. So we know that the harmonic 1 over n diverges. But what about -1 to the n over n, as n goes, say, from 1 to infinity? Well, we just have to parse this. So let's first parse it, and we get the sum as n goes from 1 to infinity of -1 to the n times 1 over n. And this 1 over n is our a sub n. And this -1 to the n is our alternator. So we just have to check, is 1 over n decreasing? Okay. And remember, it doesn't matter if it increases, then decreases, then increases, then decreases, and then it keeps decreasing forever. What we need to know is what happens at that end. So it can have a couple of bumps in the middle, but as long as it's eventually decreasing at the tail end, we can work with this. So we first want to know, is 1 over n decreasing? So how do we know if a function is decreasing? We take its derivative. So dn of 1 over n, it's just the power rule, right? So it's -1 over n squared, which is less than 0 for every n. So it's decreasing. We're good because its derivative is 0, or its derivative is negative. Now we want to know, is the limit as n approaches infinity of 1 over n equal to 0? And it is, right? As n gets really big, 1 over n gets really small, and as we approach infinity, it goes to 0. So we're good here. We have our alternator, so we can conclude that the sum of -1 to the n over n as n ranges from 1 to infinity actually converges. And that's it. So this converges. Now let's take a look at another example. Let's say the sum from n equals 1 to infinity we'll just put a divider here, of -1 to the n times n squared over n squared plus 5. Okay, so first we can parse it if we want, or we can just know that -1 to the n is the alternating part. So the first thing we want to know then is n squared over n squared plus 5 decreasing? And you can say, yeah, it is. Or you can say, no, it's not. But we need proof of it. So let's actually take its derivative. So if we go dn, we get, it's the bottom times the derivative of the top. So 2n n squared plus 5 minus the top. So that's n squared times the derivative of the bottom, which is just going to be 2n. And this is all over the bottom squared. Okay, so the bottom is always positive. So what we need to know is this top positive or negative? And when we simplify this, we get 2n times n squared minus n squared times 2n. Well, that's 0. So we have 10n over something positive, which is actually positive. So the alternating series test is inconclusive. Okay, and it's inconclusive because if we go back up to the alternating series test, it says if we meet these conditions, then it converges. It doesn't say if and only if, or it doesn't say if it converges, then it has this property. It's if the two conditions are met, then we can conclude that it converges. So right now, it can converge or it can diverge. We just don't know yet. We have to do a different test. So, so to figure out if it actually diverges or not, we have to do a different test. So let's actually look at the limit test. Remember, if I take the limit of the sequence and the sequence goes to 0, then it's inconclusive again. But if it goes to a number, then we know that it diverges. So if we take the limit as n goes to infinity of this guy here, we'll call this whole thing an. So we take the limit of an, what we get is plus or minus 1. And in either case, positive 1 gives us a number that's not 0, negative 1 gives us a number that's not 0. And so by the limit test for the sequence, we actually get that the sum of an diverges. So we actually can't use the alternating series test for this. It's inconclusive, but through other methods, we can actually figure out whether or not it converges or diverges. And in fact, testing property 2, which is essentially what this is, without the plus or minus, can give us some insight. So if we take the limit and it is not 0, then it's probably going to diverge. So I should have maybe made this step 1 and made the decreasing part step 2, because step 2 tells us a little bit more about the convergence or divergence. All right, so let's look at one more example. And for that example, we're going to take a look at the series cosine of n pi over the square root of n, and we can sum up from, let's say, 3 to infinity. Okay, so let's look at if it's decreasing or not. So we can take the derivative of cosine n pi or, well, cosine of n pi is actually our alternator, right? So this is our alternating part. So our a sub n, or the thing times our alternating part, is actually just n to the negative 1/2. And if we take its derivative, we see that this is negative 1/2 n to the 3/2. And while it's not positive everywhere, or not negative everywhere, rather, it is negative on 3 to infinity. And that's the important part, because we don't care what happens beforehand, we care what happens at the tail end. So it is negative, which tells us that it's decreasing on this interval. And now all we have to check is the limit as n goes to infinity of n to the negative 1/2. And we know that it is the same as 1 over the square root of n, taking the limit as n goes to infinity, which is 0. So by the alternating series test, we can tell that this actually converges. Okay. And just a quick note here, if we were to not have the alternating part, so we go from 3 to infinity here, we don't have the alternating part, it's just 1 over the square root of n. And if we look at our p-series test, p is 1/2. So it actually diverges by the p-series test. And we can actually do that with the alternating harmonic too. This guy here, which is actually called the alternating harmonic. So let's make that note. So it's alternating harmonic. So the alternating harmonic converges while the harmonic diverges, and this this guy here actually diverges while its alternating part actually makes it converge. So this is related to something called absolute convergence, which we'll talk shortly about in either the next video or so. But it's an important thing to keep in the back of your mind. And that's it for today. So thank you for watching. If you have any questions, comments, or concerns, leave them in the comments below. Thank you.